Hey everybody, Dr. G here. The reason I'm making this video is to introduce a computational chemistry lab that we can include in a physical chemistry lab course. So basically it's going to be, we're going to run some molecular simulations of something called a Lennard-Jones fluid. And we'll get into the details of what that means as we go, but just think of it as a simplified model of how fluids behave as interacting particles. So as part of this, I've written a code in Python that will run a Lennard-Jones simulation of however many particles you want. And I chose Python because it's a very readable language, so I think it's a nice way to introduce students to simulations like this so that they can actually kind of take a peek at the code and see what it's doing and try to understand what's going on. So for the exercise, we're going to be working in a Jupyter notebook. So I advise all the students, make sure you've installed the Anaconda software package. I'll put a link in the description of how you can get that. And then of course the code for running the simulations is a download from my GitHub page. And I'll make sure that I also include a link to that in the description. If you're an instructor who wants to start including this in your physical chemistry labs, please feel free to reach out to me from your university address to my university email address. And other than that, I hope students, I hope you have a good time doing the simulation, and let's get into it. Hello everybody, Dr. G here. Today we're going to be doing a computational chemistry lab experiment. So we're going to be working with something called a Lennard-Jones fluid. So this is one of the oldest types of chemical molecular simulations in computational chemistry and computational physics. This dates all the way back to the 50s, but it's a really useful concept and it's still used widely today. So that's what this lesson is going to be based on. We're going to do some simulations basically I wrote a Lennard-Jones fluid simulation code in the Python programming language. It's not the fastest choice of language for this type of application. Something like C or even Fortran would have been much faster. But the great thing about Python is that it's very readable. So if anyone's curious to go check out the code and look underneath the hood and see what makes this thing work, I encourage you to go ahead and look at the Python code files that are .py. So that being said, let's get into it. Okay, so as you see on the screen here, this is just a blank desktop. If I go into my downloads, so I open up my downloads folder, and I have already downloaded the zip file that has everything we need to do the simulation. So I'm going to take this and I'm going to move it from the downloads to my desktop here. So now an important thing to bear in mind is that there's been sort of a cultural shift where it used to be that you had to keep track of files on your computer and kind of know where things were. And the way that they make computers these days, in particular the operating systems, the search features work great. And so what I found is a lot of times students just kind of leave files all over the place on their computer and just plan to use the search function later to find it. Well, for this type of work, for doing programming, computational chemistry, this sort of thing, you really need to actually know where your files are. So the first thing I want you to do is take the zip file that you've downloaded and put it somewhere that you can easily find it from your desktop. So for the purpose of this video, I'm just going to keep it super simple and leave it on my desktop. Double click it, and now there is the folder. All right. So there's a folder. Programmers, computational chemists, people like that would call this a directory. But this is where our stuff is stored, right? And we see that the full name of it, LJ Simulation Lab. That's for Lennard-Jones, right? This is a Lennard-Jones fluid. So if I double click that, open it up, we see there's a bunch of files in here, right? So these files here, these .py files that I mentioned, these are Python codes that I've written for doing the simulations. And there's different ways to open them up. You could open them up in a text editor if you wanted to. If I just right click on this, open with text edit. So there's some of the code that makes this thing work, right? But what we're actually going to be interacting with for this exercise, you can do that. If you want to check them out, I encourage you to, which is one of the reasons why I wrote this sort of very stripped down molecular simulation that basically it's sort of the simplest molecular simulation I could write that's doing something real, like that's not so simplified that you can't really learn from it, but it's sort of the simplest thing that you can really get a feel for how molecular dynamic simulations work. So yeah, so these are all the different functions. We can talk about that a little more later. But right now what we want to do is we want to open up the Anaconda. So as part of the instructions for this lab, you need to install Anaconda first. So what's Anaconda? Well, Python, the programming language, basically there's a lot of different functionality in Python that you can use to do all sorts of things, you know, from doing image processing, machine learning, data visualization. There are so many Python libraries that people have created to help you do things in Python. So if you tried to load all of Python's functionality, everything anyone's ever contributed to Python at the same time, your computer would probably crash and you'd be wasting memory like crazy, right? It probably couldn't hold it, and even if it could, it would be silly to waste computing power loading a bunch of libraries you're not going to use. So the idea behind the Anaconda package for Python is that it's sort of like Python's greatest hits, right? You take a lot of the things that are really popular to do in Python and put them together in a single package that people can just download and just use it. So, you know, it's a really powerful Python package, so it's a really big snake and Anaconda. So it makes sense, right? So the first step that you need to do this lab is to install Anaconda on your computer. And I'm not going to go over that now because I've actually already made a video on how to do that. So I will put a link to it somewhere on the screen that you can click on, that if you've not yet downloaded Anaconda, you need to do that first before you can proceed with the lab. But since Anaconda is already installed on my computer, let's just get right into it here. So this little symbol down here looks like sort of a snake eating its tail. I think this is actually kind of an ancient symbol. I don't know this history of it, but I know it's been around a while. So if you click on that, that's going to open up Anaconda Navigator. So let's see here. It's still opening. There it is. So this is the Anaconda Navigator. And as I said, Anaconda is a whole bunch of different Python packages that you can use to do all sorts of different things, all sorts of software tools. And the one we're going to use today, for the most part, is Jupyter Notebook. So that's this thing right here. Not Jupyter Lab, Jupyter Notebook, this one. Now, an important thing to know about Jupyter Notebooks is that they actually open up in your browser. So this is actually a really clever idea. Basically, there was already plenty of software out there for creating websites, right? So you can go to somebody's website and look at their pictures or whatever it is that they're doing with their website. All that software was already out there. So the idea was, why not create a programming environment that uses that browser? Because then, you know, you have access to everything a browser can do in that programming environment. It's a really great idea. So that's sort of the background with Jupyter. And because of this, we need to open up our browser. So I have this browser window open up here. And so this is just, you know, blank. I'm using Google Chrome. Works fine. And here is Jupyter Notebook. So now if I click on Jupyter Notebook, I click launch, right? This one right here in the center. Launch. There we go. This thing opens up in the window. So now notice this little thing. This is a terminal. It's something that maybe you've worked with, maybe you haven't. If you haven't, don't worry about it. And by the way, if some of your classmates are moving through this very quickly, it's probably because they've done some programming before. You know, maybe they took my Chem 101 class before, or they've just done some programming in somewhere else. But whatever you do, don't let that intimidate you. All right. If it's taking you a little longer because you've never done any of this, keep going. All right. Like, because everyone can get good at this, but you know, we all started at a different spot. So, you know, that's an important thing to remember. And it's something that kind of tripped me up when I was an undergraduate. So I always try to make mention of that, you know, don't get intimidated if other people have kind of, they're picking it up very quickly, or it seems like they're picking it up very quickly, because it's probably actually just that they've done it before, done something very similar before. Okay, so back to the lesson. So this thing right here is a terminal. Maybe you've seen it, maybe you haven't. Who cares, right? But basically, this is what's running the Jupyter Notebook. So don't try to close this thing. Just leave it alone. Ignore it. I'll move it over to my other monitor because we don't need it for anything. So now, looking at this thing that opened up. So when I clicked on Jupyter, it opened this thing. Well, this is in my browser, so it kind of looks like it's on the internet, right? But it's not, right? It's just on my machine, on my computer. the Jupyter Notebook software is sort of hijacking the browser to do its bidding, right? It's getting the browser to do this, but this is not on the internet, right? This is locally on your computer. So then what I need to do is I need to navigate. Remember I mentioned you have to know where your files are? So this is perfect case in point, right? So if you look at all this stuff, basically this is a level higher than my desktop, right? So if you click on desktop here, you see how right here it says desktop, right? I'm going to click on that, and it's going to show me all this mess of things on my desktop. Now, what did I call this thing? LJ Sim something, right? Let's look for, there it is, LJ Simulation Lab. I click on that. And now if you look at everything that's listed here, and we look at everything that's in LJ Simulation Lab, we see all the same names: math tools, visualization tools, right? These are a few of the Python programs that I wrote to have some functionality that we would need for this exercise. That's what these .py files are. But the one we want to open is the .ipynb. So it's for IPython Notebook. Basically, Jupyter Notebook was originally that. So this is the file extension, right? Like if you have a Word document, it's .doc, right? Same idea, but this is .ipynb. There we go. So if I click on that, now I've opened up the simulation lab here that we're going to be doing today. So if we look at this thing, we see that there's some kind of like nice looking text, right? And it kind of looks like it's a website, right? But as I said, it's using all the tools that are in the browser to make things look nice, right? And then you look at this code block, and maybe this block right here looks kind of more like code, and it is code. So basically, what this notebook is, this is where you're going to be doing this assignment. You're going to be working directly in this thing. And when you're done, the thing that you turn in is the file that you're being shown here, right? So what we're looking at here is stored in this file here, right? This Lennard-Jones Fluid Lab. And if I want to make any changes, right, it's this little save button right here. So basically, we've got any changes I make to this are saved in that, right? Just like if you were working with, you were writing a paper in Microsoft Word and you need to submit something, right? You have that little icon that shows you where the file is. It's the same thing. But the main thing to remember is this is not on the internet, right? It just looks like it is. All right. So here we describe some of the learning outcomes and things like that. I'm not going to read it to you. You do need to actually read all of this stuff, right? So I'm not going to read you everything. I'm going to focus on going over the things that I think we'll need to do together that I think maybe you'll need more help with. Because basically, the target audience for this lab, right? The students who are going to be doing this lab, I'm assuming that you've never programmed before. So if you have, and this is really easy for you, great, good for you. But if you've never programmed before, then basically this is going to be self-contained. Everything you need to know is in this lab. And basically, there's different approaches to teaching computational labs. Some people aim to do sort of more fancy, realistic calculations, but then you can't see any of the code that makes things work, right? I'm taking the opposite approach. I'm saying let's work with a simpler system so that you can have a better idea of how things work. So that's why we're taking this approach. That's my strategy here of why I am going to make you write some Python code. Because I think it's a very readable programming language that if you've never coded before, it's a very good one to start with. So yeah, if maybe this is your first time programming, then, congratulations. This is good. You want to be doing this. This is a great skill to have. And, hopefully maybe some of you keep doing this later, if you decide that you like it. So let's see here. Definitely everyone read the student learning outcomes, right? Because this is the whole goal of why you're doing this. Okay, there's going to be a link to the video here. So if you're watching this video, then I guess you don't need the link. And the video doesn't have a link because I'm recording it now. So there we go. That's that. Let's see here. As I said, when you submit the assignment, you're submitting this file, right? That .ipynb file that we're going to be, making changes and saving by hitting the save button there. And please don't forget to save your work, all right? Let's see. Okay, I've talked about some of this stuff. All right, so let's talk about the Lennard-Jones fluid a little bit. So as I mentioned, this model has been around for a long time. All right, we've got this paper from 1957. I believe this is the first computer simulation using Lennard-Jones fluids. And you know, a lot's changed since then, right? Your phone is more powerful than, you know, that room-sized computer that they probably ran this thing on. But nonetheless, it's a very useful model for basically simulating very large systems of interacting particles that behave like a fluid. In fact, if you've ever seen like simulations of water in like video games or things like that, there's, you know, it's a very complicated field of writing the software that does that sort of thing, but it's definitely related. Like underneath the simulation that shows you something that looks just like water. Like if you look at like a recent Disney or Pixar movie or whatever, the water looks almost like you can barely tell that it's a cartoon. And yeah, there's particles underneath that, and then they have ways of rendering it so that it looks more like a actual liquid. But yeah, these particle simulations are still very much alive and well. So let's talk about the forces here. So if we talk about potential energy, if you think about two particles of some gas or, you know, some fluid, right, which can be a liquid or a gas, both are considered fluids. So if I take, let's say, two argon atoms and I squish them together really tight and push those nuclei together as close as I can get them, the potential energy should shoot up really high, right? So then if I let go of them, then they can go flying apart really fast because, you know, those two positive nuclei do not want to be right next to each other like that, right? So we expect the potential energy to go really high if I squish them together. And if they're super far apart, like let's say a few hundred angstroms apart, they probably don't really care about each other at all, right? If you kind of move them a little bit from, you know, 200 angstroms to 201 angstroms, we don't expect to see the potential energy change very much at all. But then, of course, we also know about van der Waals forces, that, you know, particles that are kind of close enough to interact, even if they don't have a charge, right, they get attracted to each other through what we call van der Waals forces. So basically, we need a potential energy function that behaves like this, right? Super far apart, they don't care. Super close, they hate it, right? And then there's some in-between realm where they kind of like to hang out. And we can actually think of this as a bond, where they have, you know, these van der Waals bonds. That's basically what this function does for us, right? This is the formal definition of Lennard-Jones potential right here, where you know, this potential energy is a function of Rij. Well, Rij is a distance. It's a distance from particle I to particle j. So like I was saying about squishing these things apart or pulling them apart really far apart, that's what that is. That's that measure. What's that distance? And we see that basically we have these two terms, sigma over r here to the 12th and here to the 6th, and it's a difference, right? So basically what this does is it gives us a shape. And we're going to do the plot, actually, where we'll look at what this function looks like, that basically, you know, the energy has the right characteristics that we're looking for. So what are these parameters? Well, these parameters, we can tune them to get our system to behave like different fluids, right? So if maybe you're working with argon versus neon, something like that, right? You're going to have slightly different parameters for these two values here. So that's what a Lennard-Jones potential is. And then basically, if I want to do a Lennard-Jones fluid, that just means that I have a whole bunch of particles, and every single one of those particles interacts with every other particle using a Lennard-Jones potential. So basically, if I want the energy of one configuration, you know, so let's say there's, I don't know, 10 particles, right? There's 10 particles, and I want to know what the potential energy is. Well, I take one of those, you know, measure the Lennard-Jones potential energy of that particle with every other one there, the other 9, right? Then grab another one, then do the other 9, right? So you can do all of these interactions with every possible set of pairs that you can make, and that's how we get the potential energy of a fluid. And basically the forces come from this potential energy function. In fact, if you take the negative derivative of a potential energy function like this, that's what'll give you the force. It comes from the negative derivative of the potential energy function. So basically, if we think about this, right, I said that the energy should steeply increase as we squish them together, right? Well, that means that if it's getting steep, that means a slope. Steep slope, strong force, right? So then the force is really pushing them again away from each other very hard. In fact, if you'll forgive me skipping ahead a little bit, I want to just show you a picture of the Lennard-Jones potential because I think it'll be helpful for you to see what's going on. So I'm going to run some code real quickly. I'll explain how it works later, but for now, I'll just run it so I can show you the picture. Let's see here. quick note about Python. You see how these statements have a pound sign in the beginning, or a hashtag, whatever you call it? That means it's a comment. So I can write anything I want if there's this comment here, and then the Python interpreter, the thing that makes the Python code run, ignores it. It says, oh, this is just a comment that the programmer left for themselves or for their colleagues or whatever. So that gets ignored. So sometimes what I'll do for this particular notebook, I'll leave commented things that you're supposed to uncomment and then run it. So that's what I'm going to do here. So I'll explain what this code does later, but let me just run it for now so you can see this image. This image is a picture of a Lennard-Jones potential. So now, so what are we looking at here? Okay, well, the potential energy is the blue line, and the distance is along the x-axis here. So this is what I was talking about verbally earlier, right? If I squish these two things together so that the distance is very small, potential energy jumps up really high, right? And we can get even closer, right? And make this go even higher. But then if we pull it apart really far, well, now the potential energy just goes to a constant. So basically, you know, again, to kind of give numbers, if you've got two of these Lennard-Jones particles and, you know, one pair is 300 angstroms apart, the other one's 500 angstroms apart, the potential energy value is going to be about the same. That's really not going to matter all that much, right? So that's the idea. Is that so really far away, they don't care. Really close together, they absolutely hate it, right? They hate that. The potential energy goes really high. And of course, I mentioned the force, right? The force is the slope here. So basically, or the negative of the slope. So basically, this is getting really, really steep. So then it pushes away, right? It has the steeper it gets, the more the force is pushing the things away. So this is the relationship between potential energy and forces. In a conservative field is what we call this. So yes. So now let's look at this kind of in-between region. So if we're hanging around here, now we see this distance. This is the minimum energy. So the minimum energy is not a pair of particles just completely ignoring each other. The minimum energy is actually when they're kind of hanging out in this happy medium here. And so basically what's going on here with the forces here is that the forces are kind of balancing out, right? The forces that want to push it apart, right? The ones that get really strong over here are at a minimum here, right? And then those sort of attractive forces that make them want to stick together, right? That's bringing it down to here too, right? So basically one's an attractive force, the other one's a repulsive force. And if you're hanging around the minimum here, then basically you're at an energetic minimum, you're at a stable point. So that's a little bit about the Lennard-Jones potential. And once again, we can have many pairs, or we could have many particles that follow this type of potential energy behavior. And all of them interacting together, we can call that a Lennard-Jones fluid. All right, so now let's go back up. Okay. So now the microcanonical ensemble, what am I talking about here? This is something from statistical mechanics, which is related to thermodynamics. It's part of physical chemistry and physics. It's, you know, there's physical chemistry and chemical physics overlap strongly in this field. So the microcanonical ensemble, this is a collection of particles. And I'll let you read about the details there. But just know that the system we're working with here is a microcanonical ensemble. And take the time to really read this and understand what I've written, because you're going to need it for some of the questions. And also, it's really going to give you a better understanding of what's going on. But I don't want to make the video longer by me reading this all to you. So, okay, so basically we're working with a microcanonical ensemble. It's a collection of these particles that the main thing to know is that the number of particles is constant, right? So they're in a container. Nobody can come in, nobody can leave. So the number of particles is the same, and it's a rigid container. So the volume cannot change. The volume doesn't change. And also the total energy in the system is also held constant. So no energy in, no energy out, right? Adiabatic conditions. Nothing can come or go in terms of energy or particles. And the volume can also not change. Which is actually, I have an important note on the microcanonical ensemble and temperature right here, right? And the reason I put that there is that if you're holding the energy constant, you actually can't hold the temperature constant. So I want you to read about this because it's kind of an interesting thing to think about. And so sort of an important thing to know when you run these simulations is that we give them an initial temperature, right? Temperature depends on the velocity of how fast particles are moving around. And in terms of these spherical particles we're working with, it's just translational motion, right? How fast are they zipping around, right? That's you know, the hotter it is, the faster they're going, right? That's basically it for temperature. But if the total energy is constant, right, we can't hold the temperature constant. So if the temperature only depends on how fast things are zipping around, well, what if some particles are zipping around in opposite directions, they come really close together, and then as they get closer and closer and closer, they slow down, right? It's almost like, you know, if you're coming up against a spring, right? You're running and and then you turn around and you get shot off by the spring, right? Back and forth. Or think of a trampoline, right? You jump on a trampoline. As you're sinking into the trampoline, you're going slower and slower because your kinetic energy is turning into potential energy in the spring, right? So basically, you're slowing down so that some of that energy can go into the spring. So the same thing happens in this simulation. As these things come together, some of that kinetic energy of them moving is going to go into compressing them. And then if things are going slower, the temperature is lower. So you actually can't hold the temperature constant in the NVE ensemble because the energy is constant. So I want you to understand that. But think about it. Read everything that's here. That should help a little bit. But I thought I'd give you a quick description of that. Okay, loading the libraries. So now if we look at section 1 here, what we're doing is we're loading the libraries from Python that we're going to need to use. And so this is what I was talking about in the very beginning, where I said Python can do so many different things, and we can't load all of it at once, right? Our computers probably couldn't hold it, and it would slow it down for no reason, right? So we load only the things we need. So I've already done this for you, right? So I've created this cell. We're importing numpy as NP. NumPy is numerical Python, is what it stands for. That basically doing different numerical operations. So say like taking the square root of something, right? That's a mathematical operation. That's one of the things you can do with NumPy. There's so much you can do, but that's one small thing. We're also brought in some other things like pandas, matplotlib. Matplotlib is for making plots. Pandas is for storing, you can do a lot of data science type things with it. We're going to use it for storing data. We'll get to that later. And now some of these things here, classes, visualization tools, dynamics. These are libraries that I wrote. So not only can you import libraries that are publicly available, libraries that came with Anaconda when you downloaded that whole package, you can make your own libraries. And so that's what I've done here. So we're importing some things there. But the main thing you need to do with this, don't change any of the text in it, right? We need all this the way it is. But if you click so that your cursor is inside this thing, do you notice how it says code right here? And if I click on this one, notice how it says Markdown, right? So this is a Jupyter thing that we all need to be aware of. There's different types of cells. So as you see, like as I scroll through this thing, I can click on these things, and these things are called cells. And a Markdown cell is a cell for making things look nice and readable. It's for giving people things to read. And so that's why the font looks really nice. It looks like more like what you would see in a textbook or something. But if you click on this is a code cell. This can be executed. So if I click so the cursor's in this box, right? And then I click Shift Enter, Shift Return, whatever your keyboard says, right? You see it? So that's how I execute a code cell, right? So you click in the box, click Shift Return, and then it executes that cell. I can also execute a Markdown cell. So if I wanted to edit this Markdown cell, what I do with the cell is first double click it. Watch what happens. So now like that nice beautiful text, it looks like this stuff, right? So this is Markdown code. You know, it's vaguely related to like HTML, the stuff that you do for making websites, right? So if we look at this, how do I go back to making it look nice? Well, you probably guessed, right? Shift Return. So if I hold down Shift and press Return, it goes back to normal. All right. So if you're working on this thing and you accidentally double click and you're like, oh my God, why does it look crazy? Right? It's okay. Stay calm. Just make sure the cursor is in that box. Shift, return, back to normal. All right. So all the instructions and stuff that I give you for the lab are going to be in Markdown cells. And when you have to write some code to do some stuff, it's going to be in a code cell. So for this one, all you have to do is execute it. Shift, return. I've now loaded all of these Python libraries that I need to do. Okay, so Prelab question 1. What's going on with this one? Let's see here. Okay, so for this one, when we got to this originally, right, it was like this. It was commented out, right? So with these comments, if I hit Shift Return, see how the plot went away? Because now these are just comments. Python just ignores these. But if I want it to actually execute this as code, I need to get rid of those asterisks, or not asterisks, pound signs, shift return, and now it did the thing again, right? So what it did here, first it created an object that we're naming sample, and the object type is ensemble. So it created this thing that I've just called it sample, and then I'm using one of the libraries I wrote to plot things. And my library calls another library called matplotlib to do most of the work, to be honest. But so yeah, so the plotting and basically all the plotting that we're going to do in this exercise, I basically give you code to do that. So don't worry too much about it. But see how I say import visualization tools as viz. So then if I want to use one of the functions from that, which plot LJ potential, plot Lennard-Jones potential, that's what I named the function. So to access this, I have to go viz dot, see that period right there, and then the function that I want to run. I have to do both of these things. And then if I do that, yeah, it'll run. So basically, that's what's going on here. So an important thing to note about programming languages is that some of them are considered object-oriented. So you can Google that if you want to read about what object-oriented programming languages are. But basically what we need to know here is that some programming languages organize things by creating something we call objects. So what's an object? Well, in this case, we have an object that we call ensemble. So remember I mentioned that if we have a group of particles, we call it an ensemble, right? And the one we're working with is called a microcanonical ensemble. So I created an object called ensemble that has all sorts of properties. So for example, let's put another code cell. So with this code cell here, if I want to make a new code cell, hit the plus sign. So now I've got a new code cell here. If I wanted to switch it to a Markdown, I could hit this. Now it's a Markdown cell, right? So if I want to make that nice looking text, now it's Markdown. Go back to it, double click it. I'll delete all that, and then I'm going to switch it back to a code cell. Now it's code cell again, right? So I've created this object called sample, and the type of object it is an ensemble, right? So like, if, okay, so if you name your car, right? If you're the sort of person that names a car, right? Let's say you have a Mustang and you name the car Julius, right? So then you could say you have an instance of a Mustang. That's the type of object it is. It's a Mustang, but that specific one is named Julius. Same idea here, right? So I have ensemble is like Mustang, right? It's something that you can make these things, you can make a bunch of them, right? This specific one is named sample. And by the way, with programming, things always go from right to left. So basically, so equal signs in math classes, we're used to that kind of being a symmetric thing, right? We can move things back and forth across the equal sign. Not so in programming. Very different thing in programming. Programming, the thing on the right gets assigned to the left. So never forget that. Okay, so we've created this thing called sample. Let's see what kind of information sample holds. So just like if I had an object that is it's a Mustang and it's named Julius, I can check and see the color of Julius, right? So that could be something I would do. So then it would be like Julius.color, and maybe it would return orange, right? So for this one, what if I go sample.temperature? And by the way, because I knew that temperature was one of the names here, I actually just typed temp and then I hit the tab key and it auto-completed it, right? So that's another thing, is that if you're typing something that's unique, basically there were no other names that started with TEMP, so then Python actually knows how to finish the word, so you just hit the tab key. Good trick. So now, if I execute this now, I go Shift, Enter, it returns 1. So the temperature was set to 1 Kelvin for this particular ensemble. So you notice how in the parentheses I don't have anything for the temperature? That's because we're just going on default values. I could do temperature equals 5, right? If I did that, and then I check the temperature again, now it's 5, right? So we can change these things. Basically, I just kind of wanted to show you what an object is, that I can check. See, now it's back to 1 because I redefined it. And by the way, until you execute a cell, it hasn't taken effect, right? So just by typing, temperature equals 5, right? Right now, if I execute this, it's still at 1, right? But if I first execute this, then execute this, Now it's 5, right? So that's an important thing. So you should have things that run from top to bottom, right? If you're creating something like this from scratch, I should be able to just run the entire thing in order and it works, right? So important thing to remember as well. But for this particular project, I've kind of put it together in such a way that you shouldn't have to worry about that too much. Basically, everything's kind of given to you. It's more paint by numbers, right? You're kind of filling in the blanks as you go. I don't know if people still do paint by numbers. Anyway, okay, so that's a little bit about objects. Now let's get into some pre-lab questions here. Okay, so let me get rid of this temperature equals 5 here because we just added that for the sake of conversation here. All right, so pre-lab question 2. So take a moment to read this, maybe pause the video, read the question, and let's see here. Let's see what we need to do. So basically, I'm going to assume you've already read the question and talk quickly about it. So let's see. The first thing we need to do, we need to find out the values for sigma and epsilon. Okay, so basically we can do it with this one that we called sample here, right? We have this thing called sample. So let's find out the values of sigma and epsilon for sample. So I'll give you an example here, right? That if we had an object named Bob, right? And there was an attribute called epsilon, you say bob.epsilon, right? Just like we did above, right? Sample.temperature, same idea. But we know we called this thing sample. So let's go sample.epsilon, shift enter. There we go. Epsilon value is 1. So we know epsilon is equal to 1. And now let's check the same for sigma. Sigma, also 1. Okay. So that's how you do that part, right? So you get these values for sigma and epsilon. I'm not going to do the math for you here, right? That's your job. But now you need to plug these values into the Lennard-Jones potential energy function. So that's, where is it? There it is. So this right here is an epsilon, and this is a sigma, right? So if you plug in a 1 for both of those values, then I want you to take the derivative of that, and basically you're going to figure out where this sort of happy point is, right? The stable point, right? This is a our energetic minimum here, right? This is our stable point. So I want you to figure out where that is, and just kind of looking at with our eyes here, we see that it's more than 1 and it's less than 1.25. Okay, we can see that by eye. So when you do the algebra and figure this out, if you don't get a number that's between those two, you're wrong, right? So keep working at it. That is that. I think that's all you have to do for this step. Yeah, okay. Now for the next step. So for pre-lab question 3, again, pause the video, actually read the question, then go back to the video. Otherwise, what I'm saying isn't going to make sense. Basically, what we want to do here now is, this is kind of more of an intuitive question, but the first thing you have to do is just get rid of these pound signs so that you can see what's going on. So I'm just going to do that and show you the image. So these are the two images here, right? So the top one here is this top code. The bottom one's the bottom code, right? So we've switched sigma from 1 to 2. We've changed our sigma value. The other thing we've done is I've changed the cutoff value. The reason I did that is because this plotting function uses the cutoff value to know how far to plot in the x direction. Right, so this one stops at 3, this one stops at 4, but this goes 1 to 3, this goes 2 to 4, so they're covering about the same amount of ground here, right? So as for answering this question, that's up to you to figure out. I want you to really read this, think about how these things work, and use your own intuition to answer this question. But I want to make sure that I show you just how to produce the plots. So those are the plots. Okay, pre-lab question 4. Let's see. Okay, so now for this. For pre-lab question 4, you see we have a 2-dimensional particle area and a 3-dimensional particle volume. So the reason we're thinking about this is because later in this lab, we're going to be dealing with the van der Waals equation, right? We have Remember, that's sort of the corrections to the ideal gas law. We have the ideal gas law that assumes that all of the gas particles are points, right? These points don't take up any space themselves. They pass right through each other. That's what's going on with an ideal gas. Whereas a van der Waals equation says like, well, that's not actually true. It's a useful approximation. You could do a lot with the ideal gas equation, a whole lot. But if you want to get a little more precise, maybe we should make sure the particles take up a little space, and perhaps they're not indifferent to each other. Maybe they're a little attracted, right, to each other, or repulsive, right? You can kind of go either way with that equation. So that's the van der Waals equation. We're going to use that later. So what we want to do now is we want to get some sense for the volume of these particles. How much space do these particles take up? And, in reality, these things are kind of squishy, right? Which we talk about in the previous question. So if we want to think about the volume of these things, if you put two of these particles next to each other so that they're just touching and basically they're in this sort of happy medium, right? They're hanging out at this energetic minimum. The distance between those 2 points, when they're just kind of chilling like that, how far apart are those points? That should be twice the radius, right? If that's the two distances, right, that should be twice the radius. So basically you can figure out the radius, and then from there you can figure out how big the particles are. And again, they do have some squish to them, right? They have a certain volume, right? Like if I took two volleyballs, I could squish them together, right? And you could see them deform. So the centers of the volleyballs, I could make them get closer together. So even though a volleyball has a definitive size, it's squishy, right? Whereas two billiard balls, I can't do that. So the Lennard-Jones fluid here is more like the volleyballs, less like the billiard balls. In fact, hard sphere simulations, more like billiard balls, has been done to simulate liquids as well. And those are even more computationally inexpensive than these, right? So, but that's a different thing, right? We're doing a Lennard-Jones simulation. So, but just know that hard sphere simulations is another way to approach liquids. Okay, so I want you to find both a two-dimensional and a three-dimensional solution here. Okay, so now section 2, simulating dynamics for an ensemble of molecules. So here we're actually going to do a simulation, right? So far we've kind of talked about it. We've done some calculations. We've actually even created an ensemble object, right? We've created an object that holds a bunch of molecules in it. And we've accessed some of the information like the temperature. But now we're going to take one of those objects and actually run dynamics on it, right? So if all of those particles, each one has some initial velocity, and you let it just go, you let it move forward in time, then these things are going to fly around, bounce into each other, etc. So we want to see that happen, right? It's pretty cool. So for this particular, the first simulation, I give you all the code. It's just commented out. All we have to do, in fact, let's do that. Let's go through and turn off all of these comments. Or not, just to uncomment them, we call that, right? If you make them run like code, get rid of the pound sign. Okay, Command Z is undo, right? Always know what undo is on your computer. It's a keyboard shortcut you really need to know. The amount of time it takes you to get that memorized will save you years off your life later. So, okay, let's see. So now I've uncommented both of these things. And before I run this, I want to just show you real quick our directory, right? This is the folder where we're running this particular thing, right? This thing is this, right? That's the icon for this thing, right? So that's where this is. And the reason I'm showing you this is that when I run the simulation, it's going to produce more files in this same directory. So again, this is why you really need to know where your stuff is, right? So, all right, let's run this first one first. Shift Enter. This just initialized my system. We see that this time we gave the ensemble a few parameters. We didn't just let it run on default stuff. So just real quick, let's look at what we did. Nmol, number of molecules is 25. The side length is 10. So this thing is in a box. They're going to be bouncing around inside of a box. And the length of one side is 10 angstroms. This is hard to look at, so I'm just going to, give us a little more space here. There we go. So if we've got side length 10, that's the side, the length of one side of the box is 10. the dimension is 2. We can control how many dimensions our simulation is. So are these particles bouncing around in a 2-dimensional space or 3-dimensional space? Right? Obviously 3-dimensional is the realistic one. But the nice thing about 2 is that it can be simpler to think about as you're trying to get an understanding of things. And it's also really simple to do visualizations of. So you'll see what I mean. So we're going to start on just 2 dimensions. So imagine you have particles that live on a sheet of paper. And they can bounce around just like a fluid and run into each other and run into the sides of the container, etc. But they can't leave the paper, right? They're living in 2 dimensions. Let's see here. Now periodic, we've set that to true. And we've set, and we'll talk about that more in a moment. These are periodic boundary conditions, if you want to Google that, what that is. And then use LJ is true. So use the Lennard-Jones potential. Yes, we want to use it. And our temperature, we set it to T init. So here we have T init. Remember, things go from right to left. So with this 1 value gets assigned to T init. So we're running at temperature 1. Okay, so I run this. That just creates the ensemble. So right now, there's an ensemble sitting on my computer that has 25 molecules in it, and it's ready for action, but we have not run a simulation yet. Now this box right here, this one I'm also, you know what, I should just expand this a little bit. There we go. I think this will be a little easier to read now. Where'd it go? There we go. Okay, so now this box right here, let me again add a little more space here. So if we look at this box, now this one, what do we have here? So we have a start time. So we're using a library called time. What this is just a timer. I want to see how long it takes to run something. So basically, I have all the code for that. In fact, I add a little space so you can see what's doing the timing, right? So here we're starting the time. Here we're measuring the execution time, right? How much time? So this tells me what time it is now. And then I subtract the time when I started, so that's the difference in time. And then we print out how much time went by. And I kind of format it nicely, but the rest of this code just makes it look nice. So it doesn't just spit out seconds, right? Okay, so in the middle of the timing stuff, this is the part that actually runs the simulation. And again, I gave you this code. This is just, all you have to do is uncomment it. But we want to know what we're doing. So yeah, we're going to run dynamics. So we have a function called run dynamics that lives in our dynamics library file, right? I wrote a dynamics code, and that's where it is. So run dynamics, we imported it with the name dyn, right? So that's why I have to go dyn.run dynamics. But again, you have this code, copy and paste it, right? Reusing code is the smart thing to do. Don't retype code if you can copy and paste it from somewhere, right? That's work smart, right? So we have this thing, we named it ensemble1. So we're going to pass ensemble1 to this function. So just like when you have mathematical functions, if you have like f of x, right? You have f and then a parenthesis and then an x and another parenthesis. X is the thing you pass to it, right? So like if you have f of x equals x squared, if I give it a 2, it gives me a 4. Functions in programming are the same way. So I'm going to give it ensemble, this thing that I made up here. I'm going to give it a number of steps I want it to run and how often I want it to save the data. So every 5th step of the simulation, it saves the data. So we have a print statement to tell us what's going on. And then we also have this function, make trajectory movie 2D. So what this does, this is a function I wrote that is actually going to make a GIF. So we can actually watch the simulation. So without further ado, let's run this thing. Shift, enter. See what tells me what step it's on. 1, 2, right? It's running, so simulation's still running. Also notice this little asterisk here. If a particular cell is running, you'll see that asterisk, and it'll turn into a number once it's done running, right? So remember this, that if something is running, it'll tell you by having this little asterisk there. So if it seems like nothing's happening, what's going on, just look for an asterisk, see if something's running. Okay, so this thing ran, it gave us this little picture here, but now let's look at the directory. This is the directory where this thing lives. This stuff wasn't here before, right? Look, we've got this KE, that's kinetic energy, potential energy, right? So we've got, it produced some data files for us, and it also produced this GIF right here. So if I right click that, open with Google Chrome, check it out. So this thing is playing in my browser. So you see how these particles are bouncing around, they're interacting with each other, right? That's the Lennard-Jones potential in action, right? They get close, they start to really hate it, and then the force pushes them apart, right? Same idea. They're attracted to each other when they're like kind of close by. They ignore each other really far apart, and they repel each other when they're really close. So this is we're watching this. This is on my computer, right? This is not on the internet. So yeah, so this is our simulation results that we just produced with our Lennard-Jones simulation. So again, that's this file, but I'm playing it in the browser. You can open GIFs with other things as well. You can text them to people. So maybe you can text people your simulation results. If I don't know why you would do that, but you could. I'm not going to say I've never done it. I've done it. So that's that. Okay. So now we've run a simulation, right? Congratulations. That's cool. And yeah, so these are all the files that made that happen, right? So a lot of things are going on underneath that you haven't seen working, but they're working for you. Okay, so that's how we run a simulation. Let's see here. Okay, awesome. So your first simulation is now under your belt. So now let's see what's next. Okay, so here we have a question about, more of a conceptual question about the simulation. So that's for you to figure out. We don't have to talk about that now. This is more about just making sure you know how to run the codes and write some of the codes. So we'll skip over that for now, but don't forget to do that. Okay, so here's another thing. These CSV files, right? So these things were created, right? And like I could open this in, let's see, I could open it with Excel. If I open that with Excel, all right, so this Excel opened up, and we see that, look, it looks like an Excel sheet, right? The CSV file, if I open it in Excel, it looks like an Excel sheet, right? We have the time step, right? 0, 5, 10, 15. Remember, we're only saving every fifth thing, right? We're saving every fifth one. And remember, we said that the simulation is saving every 5 steps. So 0, 5, 10, 15, 20, right? It's counting, it's giving us the step at which this potential energy was measured. But this is a .csv file. It's not an Excel file. But if you open it in Excel, Excel knows what to do with it. But let's just quit Excel for a moment. What if I open up the same file with a text editor? Open with text edit. There we go. See, it's comma separated values. Value, comma, value. Value, comma, value, right? So that's what a CSV stands for. So really, it's just a text file. It's just that Excel knows how to look at it. But another thing I can do, I can load this into a Python session. And in fact, I wrote a function that will do that for you. So basically, I gave you the function here, right? So you just make it not a comment anymore, execute it. And this is reading in these files here, right? So this KE and PE, kinetic energy and potential energy, and it's plotting them here. So there's some conceptual questions about this. Again, that's up to you to figure out how to do that. But just wanted to go over that those files are there, and this code is reading those files in to produce this image. And it's only, the reason it's one line of code is because I've written a function that does the stuff for you, right? And my function calls other libraries, right? It calls like matplotlib and maybe some other things too, right? But and again, you can go read it if you want. It's you have access to all the code, right? This is when somebody tells you some software is open source, right? It doesn't just mean that it's free. It often is free, but open source means that the code that actually makes everything happen, you can go look at it. So that's the idea with this, right? That's what this means. You can go look at my code if you want to see how this stuff works. Okay, so now we have to run some more simulations. But this time, the directions tell us to turn off both the periodic boundary conditions and the Lennard-Jones potential. So let's try turning off both periodic boundary conditions and Lennard-Jones potential and run the simulation below. Okay, so again, I give you the code for this one. Let's first uncomment all of this. Okay, so if we look at this thing, we have ensemble. It's still 25 particles, side length 10. That stuff didn't change. We're still in 2 dimensions. But now we said turn off the periodic boundary condition. Okay, so I turn periodic false and use LJ is false. So we're not using the Lennard-Jones potential now. Temperature we left alone. So now let's run this one. And the rest of the cell looks very much like the other one, with where we have the timer to tell us how long the simulation took to run, etc. So let's get this thing going now. That was fast, right? So it takes time to calculate those energies between the potential, the Lennard-Jones potential, right? That takes time. That's kind of, we talk about computational expense. That's kind of one of the more expensive things, is finding all those pairs of interactions, right? That takes a lot of time. Okay, so after we ran that, we see that now we have this trajectory 2, traj2, right? And if we look at the name, where is it? File name traj2. So when we created the GIF file, this function here lets us give it a file name. So this time we gave it a different name. Because if we gave it the same name as the other one, it would have overwritten it, right? It would have gotten rid of the old one. But we want to be able to look at both of them and compare. So to open traj2, that's the one we just created. So let's open that in a browser. And so it's up to you to kind of examine this thing. Right? How are the, basically the particle interactions, the interactions with the particles in the walls of the container? Take a look at it. Try to see if you can understand what's going on. But, again, this video is just to make sure you can run everything and work with it. It's up to you to do the thinking. So that's all I'm giving you. Okay. Now we're on to lab question 3. Okay. This is another conceptual one. You're on your own, right? Question 4. This one involves some code again. So this one we will go over. Okay. Okay. One of the most common data structures in Python is the dictionary. So dictionaries you can think of as holding keys and values, right? Like there used to be these things called phone books, right? I don't know if you've heard of a phone book. But yeah, I'm at that point in my life where I'm talking about things that don't exist anymore to people a good bit younger than me. So phone books were books that had people's phone numbers and their name, right? So a dictionary is like a phone book in that if you look up the person's name, that's the key, and then the value stored that goes with each key would be the actual phone number. So that's what dictionaries are. And it turns out that when you create objects in Python, they automatically, you can access dictionaries that give you all the pieces of information that we can get. So remember we talked about objects, right? I said like the car. I could name a car. I could have one specific Mustang and name it Julius, and it has a quality, right? I could say I could check its quality, Julius.color, and it outputs orange, right? Something like that. Or I could here we have dictionaries and keys, right? So basically what this does is that'll tell me all of the things. So like going back to the car example, right? If I did this dictionary keys thing on that, it would tell me everything about it. Oh, is the transmission's manual, it's convertible, the color of the seats or whatever, right? You can have all of these different pieces of information. So if I wanted to just see a list of like, what's everything I can ask about this car, that's what we're doing here, but we're doing it with ensemble 2. So the simulation we just ran, we named it ensemble 2. So if we have ensemble 2 dot double underscore, right? 1, 2, that's 2 underscores, DICT, dict, like for dictionary, another double underscore dot keys, and note these 2 parentheses, right? That's because keys is a function. If you call a function, it needs parentheses. So if I run that, it shows me everything I can ask about ensemble 2. It has bounds, it has a temperature, it has a side length, it has a number of dimensions, a sigma and epsilon, right? Those 2 parameters in Lennard-Jones. It has all of these things. So now down here, we want to use this ability to access information to calculate Boltzmann's constant. So I'll tell you that for simulations, a common thing to do is that you work in units where Boltzmann's constant is equal to 1. And we've done that here. We're doing that. So this value should be about 1. So if you get something that's nowhere near 1, you did something wrong. But basically what we're going to do is we are going to take, PV equals NKT, right? And we're going with K because the N for this one we're talking about is number of molecules, right? Not number of moles, right? The PV equals nRT. That one's better for experiments where you're working on scales of moles, right? 10 to, an order of 10 to the 23rd molecules. We're nowhere near that. We got like what? I think so far we've worked with, 24 or something like that. So we're nowhere near that number, right? So that makes sense. It makes more sense to use the other version of the equation, where instead of the gas constant R, instead of that we use Boltzmann's constant K. So, but yeah, so just swap out the R for a K and make sure that the N is number of molecules, not number of moles, and you'll be good. So let's assign some values. So if I run that, now this N is storing the number of moles from ensemble 2, right? So if I add a new cell here, let me just hit the plus sign, make a new cell. And then if I type N now, whoops, and hit enter or shift enter, right? It outputs 25, right? So N is now storing the value 25. So what you want to do now is do this with pressure, volume, and temperature, and then solve for KB here. So do a little bit of algebra and do that on your own. I'm not going to show you exactly what it is, but follow the same pattern, right? And you know the dictionary things you can use here, right? Right? So one of them, N mole, number of molecules, right there, right? So you can imagine that if you want the pressure, it's probably called pressure, right? There it is, pressure. So do that for these other things, and then I want you to put them all together here, right? So if I had N, and I'm just going to make something up now so I don't give it away. W is 5, right? If I put W times 5 here, or sorry, W times N, see how it outputs 125, right? Because this is 25 times 5 is 125. So this is what you need. Don't write W times N. Don't put a W here. You're going to find P, V, and T, and then multiply them together in the way you should multiply them together, and perhaps some division, right? So that you can get KB here. So you need to do that. But I want to make sure you knew just the Python necessary to do that. So do it in this cell. And again, remember to execute it. Shift enter is what you do. Okay. Now, section 3. Okay, now this is sort of the main event here, is we're going to basically make a model of our model, right? If the van der Waals gas is a model, right? So is the ideal gas. So models are things that we contrive to try and explain something that's going on, right? And the good ones are mathematical models, right? The models that they can really predict things are mathematical models. So we want to make a mathematical model that, you know, at least gets pretty close to predicting reality, right? That's the idea with a model. And there's varying levels of detail. I could simulate a gas, and I could treat every single electron and nucleus and treat every single electron quantum mechanically in the simulation, but then maybe not the nuclei, right? But maybe I do want to treat the nuclei quantum mechanically, right? And then this thing would get crazy expensive to run, computationally expensive. I guess monetarily too, if you think about all the computing power you might have to buy to do it. But that's not what we're doing here, right? We're using a simpler model than that. We're not taking into account all of these quantum mechanical details. We're saying basically, all right, fine, we know it's more complicated than this, but if I take two particles and squish them together, the energy shoots up really high. If I pull them apart, right? We justified the Lennard-Jones potential earlier. But it's that type of justification. So basically, one of these models that we can do to sort of approximate what's going on is a van der Waals model, where it's, you know, it's a little more detailed than an ideal gas, but you know, not that much more detailed. Whereas our Lennard-Jones fluid is a lot more detailed. But the idea with this section of this lab is say, like, okay, we're running these Lennard-Jones simulations. Can we fit a van der Waals model to that model? So that's what we're doing here. So if we want to do this, there's some parameters in the van der Waals equation. So just like Lennard-Jones has epsilon and sigma, van der Waals equation has parameters as well. It has this A and this B. So we're also going to need to figure that out. And so this is sort of the more common, you know, definition of the van der Waals equation right here, that, you know, it's in terms of R, the gas constant R, and it's in terms of N, the number of moles. But again, we're on a much smaller scale than that. So we want to be in sort of the Boltzmann scale here. And so this is a way of expressing it that way, where we still have these two parameters, A and B. But notice that volume is written as volume over the number of molecules, right? So this little v here, you notice that's a lowercase v. Every time you see that little v, that's the actual volume divided by the number of particles, right? So you can think of it as 1 over the density too, right? If you have number of particles per volume, or the mass of the particles per volume, if you have density defined that way. Same idea. But that's what the little v is. So this is the equation, and we want to figure out what these parameters are. So the first thing we want to do is we have to figure out what b is. So the reason we do b first is that if you read about the van der Waals equation, you know that it is that b is basically the volume occupied by the gas particles themselves, right? Because the original ideal gas equation assumes that all the particles are just points. They don't take up any space, right? You can have an infinite amount of gas particles anywhere you want, right? Because they don't take up space. We know this isn't reality, right? These particles actually do take up space. They're very small, but they take up space. So the idea with B here is we need to figure out the volume of one particle. So notice I say volume, not area, because now we're going to move into three-dimensional simulations. So we started out with the two-dimensional ones because it's really easy to visualize them. It's kind of easy to sort of have a nice looking visualization in Python where you saw those little blue dots bouncing around, right? But in this case, we want to be in 3 dimensions. So we need to figure out the volume of one of these particles. Well, you've already done this in an earlier question. This is why I asked you to do that, was to figure out the volume of one of these particles. So you should do that previously, right? I'm not going to tell you how to do it now. I'm not giving it away here. But whatever that value is, assign it to b. So get rid of this comment right here. Make this a b equals, I'm just going to give it a value. I'm going to say it's 0.8, right? Because you have to figure out what it is, right? I don't want to give it away. So I'm going to set it to 0.8 here just so we have a value in there. Shift enter, that's in there. Okay, now, so b is assigned. So if we do some algebra, so if we take this thing, where is it? This equation right here, right? If we take that and do some algebra on it so that we can get p by itself. If we want to just get an expression for p, I've done the algebra for you. I probably should have made you do it, but here's the p. So p equals this thing, right? So if I give this thing a and b and I give it this reduced volume, this volume over number, and the temperature, if I give it those values, it can give me a pressure. It'll predict what the pressure is according to van der Waals' model. So you use the van der Waals model to predict the pressure. So is what this equation will do for us. So it turns out sort of the kind of the most straightforward thing to do here to figure out what A is why don't we just try a whole bunch of them? Make the computer try a whole bunch of them and then pick the best one. That's essentially what we're doing. And we're going to use something called a chi-squared test. Or also known as like a least squares fit, which I know is in your lab manual as well. So we're going to use that trick here, and we're actually going to carry out the chi-squared test using Python. So that's what we're going to do. We're going to try a bunch of A's, and then we're going to plot the A value, we're going to plot the chi-squared value as a function of A, and wherever that's at a minimum, that's the best value of A for this model. So let's see here. But the first thing we need to do here is we need to run a simulation here. So first, in fact, we need to run multiple simulations really. So because it wouldn't, one could run a single simulation and have the predicted pressure and figure out the chi-squared value and take the difference between that 1 point, right? But that's not that great of an idea, right? We should probably do more than that. We should be more thorough. N of 1 is typically a terrible idea. So let's not do that, right? We're going to run multiple temperatures, which is going to produce multiple pressures, right? We'll get pressure as a function of temperature because we can change the initial temperature of our simulation. And of course, the actual temperature will fluctuate throughout, but we can give it an initial temperature and let it run. So we know that our temperature values are a little squiggly. There's a little bit of uncertainty in them there, but we can still plot temperature as a function of, or pressure as a function of temperature, and then we can find a least squares fit for the van der Waals equation, and then that'll kind of give us a good ballpark for what a good value of A should be here, the parameter A. So let's see here. Well, before we run a bunch of simulations, in fact, we're going to run 10, but let's run a single one first. So let's see. So I've given you the code here, right? So I've given you a code for running one. So let's uncomment this and run it first. So this one we're calling test sim, and we're doing the we're timing it again. So let's look at the parameters. 64 molecules, side length of 8, dimension of 3. Okay, so this one's going to take a little longer than the other one, right? Because now we're in 3 dimensions and we've got 64 molecules. I think we had maybe 25 for the 2-dimensional one, but we have 64 now. We've turned our periodic boundary conditions on. Hopefully you can explain what that is now. And Lennard-Jones, of course, we have that set to true, right? Because that's the whole point here. We want to do a Lennard-Jones fluid simulation. Let's see here. And of course, we're using our timer again to see how long this goes. We're running for 1,500 steps, so that's a little bit longer simulation too. So this might take a minute or two. Let's run it and see how long it takes. So I've uncommented everything, Shift Enter. It's running. Step 1. Okay, now it's on to the next 100 steps. So you see how long it's taking to do 100 steps, and we want to do 1,500. So it looks like this is probably going to take, you know, maybe a little over a minute, something like that. So we'll let that run. And so while that's running, also notice that we've got, and by the way, your computer may run faster or slower than this, right? This is my computer from work, and you know, I'm a computational chemist. Obviously I have a pretty fast computer, but you know, no worries if yours is a little slower. I tried to choose small enough system sizes that this should run on really anybody's machine, should run okay. But you know, reach out, you know, let me know if your computer's just not making it here, right? And then we can cut things down a little bit, either run less molecules, less steps. We don't want to go too few steps though, because it kind of takes a while for the molecules to kind of settle in and do their thing, because they start out in kind of this artificial grid shape, right? Because you have to start somewhere. So we kind of want to give them time to mix. But basically 1,500 steps I think is about ideal. Okay, it finished running. So it took 0 minutes, it took 56 seconds is how long this thing took to run. Not too bad, 1 minute. So, you know, if your computer takes 5 minutes, that's okay, right? Let's see here. But I think it should be pretty similar across computers, because I'm not doing anything like, I'm not doing any kind of parallel speed up sort of tricks or anything like that. So it should be pretty similar, I think. Anyway, okay, so we've run the simulation. We've created this object called test sim, right? This has information in it, but let's just take a look at what test sim looks like. So there's a function here. So I wrote a function called write_xyz within the visualization tools module that I created. And we're going to run that on test sim, and we're going to call the output file testsim.xyz. So if I run that, it runs very quickly. What did that do? Well, it produced a new function. See, we didn't see, or a new file, right? We haven't seen this file before, test sim. So this file now, I can look at this thing in, you know, a viewer for doing, you know, if you've ever done, if you've used VMD or Chimera or Pymol, you can look at these things there. Unfortunately, it looks like Chimera does not like XYZ files that have more than one configuration. So these are changing in time, right? So it's animated. Chimera doesn't seem to like that, but VMD and Pymol work great. I'll open up with Pymol. Open that up. Okay, Pymol opened. I'm going to type zoom center 11. So kind of change the point where it's zoomed at. So here's my particles, right? See how now we're in 3 dimensions, right? Before we just had that square grid because they were just moving in 2. Now we're in 3, so we need something like this to look at it. So I can run that. We can see these things bouncing around as spheres. So that's kind of neat. And you notice how you see things kind of popping in and out on the sides, right, from the periodic boundary conditions. All right, let's take a look at it as well in, let's look at it also in VMD. I think VMD, I actually kind of prefer for this. So let's see, I'll open up VMD also. Okay, so now I have it open up in VMD. I think this is really cool because it has something called dynamic bonds. So basically when they get close enough that they're forming that bond, remember that sort of happy point, it shows a bond. So if we start the animation, right, we see them bouncing around. Let me slow it down a little bit. So now we see the particles bouncing around. I think this is so cool to watch. So this is a, you know, short simulation, small. You know, you could make these things a lot bigger if you wanted to run it for longer. Yeah, so I just wanted to kind of show you that when we run a three-dimensional simulation of the Lennard-Jones fluid, this is what's happening, right? These particles are bouncing around. Basically, VMD, the software I'm using to show you this, I told VMD that these are argon, right? So I just said, they're argon, right? So then VMD is like, okay, argon. So it puts them in here, and that's why we can do this visualization. So that's a way to look at it using VMD. So if you've used Pymol or VMD before and you want to try looking at them, go for it. Have fun with it. But I thought this is kind of a cool way to show you. So you don't have to do the visualization in VMD or Pymol for credit for the lab, but it's worth seeing this because I think it's just cool. Okay, so we did all that with this XYZ file, right? So I wrote a Python function that writes an XYZ file. But if we look at this thing, so we opened it with Pymol and VMD. Now let's just look at it with a text editor. If we look at this thing with the text editor, this is all we have. So we've got numbers, X, Y, and Z. These are coordinates, right? Cartesian coordinates. Remember those things? X, Y, and Z. And in the first column here, we see the type of atom. So again, remember I told you that I told VMD, I was like, it's argon, right? So I just had it write this file where we write, 64 is the number of atoms. And then you say it's an argon and where it is, X, Y, and Z. So that's just this over and over again, X, Y, and Z, X, Y, and Z. So when I pass that to VMD, VMD knows what to do with it. It says, yes, this is an XYZ file, and these are argons, and these are the positions. I know what to do with this. So just by producing this simple XYZ file with Pymol, then I can open that file with some of these fancy visualization tools like VMD and Pymol. So I thought that was worth checking out. Okay, so we have a code here that's going to run one simulation, right? And we're going to take this code and we're going to run it a bunch of times, right? Because we need 10. We have to run 10 simulations if we want to do a good job with fitting the model, the van der Waals model, right? Okay, so first we need to define a temperature range. So here we use a NumPy function called linspace. So what this is, we'll define it here, right? So we have temps, and we're going to print temps. So if I just set temps to 5 and print it, that's what this cell does, right? But that's not what we want. We want 10 temperatures, and the instructions say we want 10 temperatures ranging from 0.5 Kelvin to 2 Kelvin, and we're going to use a NumPy function called linspace. Okay, so NumPy, when I imported it as NP, the letter NP. So I said import NumPy as NP. That's way in the beginning of this thing. So because of that, I have to type NP and then dot, and then I can use this linspace thing. In fact, I type LINS and then I hit tab. It finishes it, right? Because that's the only function in NumPy that starts with LINS. Then I hit a parenthesis. And the way you use linspace is that you give it the range and then how many steps you want. So if I say, what do we say, 0.5 to 2, and I want steps, or I want 10 of them. So I type 10. Now if I hit Shift Enter to execute that, see I've got a list of temperatures. 0.5, 0.6 repeating, etc. We go all the way up to 2. So it did exactly what we wanted. We got 10 temperature values. So that's how you get your 10 temperature values. And this temps is called a list, because this is an object too, right? And if you want to find out what type of object something is, the command is type. You just type, type, right? TYPE. And then in that, you put the name of the thing you want to check out. So I want to know what temps is. I put temps in there, Shift Enter. It's a NumPy array. That's what that means. So it's like a list of numbers that we can do things with. So that's what we have here. So it's a NumPy array. I think I said it was a list. It's actually a NumPy array. They have some similarities, but they are different, definitely. Okay, so now running the 6 simulations. This is a little bit tricky, but we'll figure it out together. All right, so this part is a little tricky, and this is one of the main reasons why I made a video to go with this, is because this is something that, okay, if you've been programming for a while, maybe it's not that tricky, but this lab is for everyone. This is for all PChem students, right? You have to reach that level of your education to really follow this well, I think, but not necessarily having ever coded. So we're gonna code it together here. So we want to run 10 simulations. There's a device in programming called a for loop, right? And this is a motif. You see it in like most programming languages have a for loop. So it's kind of easier to just show you what a for loop is than to describe it too much. So let's say we have these temps here, right? So let's say this is an array of temperatures, right? So you can think of it as a list of numbers, right? And basically we go through there. Let's say we want to print out the value for each one. So I want to go through this list, and when I get to the value, print it out. So if I want to do that, let's write a for loop that does that first. So the way you do it in Python is you say for t in temps. Whoops. And I could have called t anything, right? I didn't have to call it t, but give it something that makes sense. So t in temps. So each temperature in the temperature list. Then you say what you want to do every time you get to that. So basically, as I loop through this thing, wherever I am in this list, I refer to it as t, right? So here's t. First t is 0.5, then it's 0.6 repeating, then it's 0.83 repeating, then it's 1, right? So as I move through it, the thing that I call t changes. So that's what a for loop does for me. So here we have for t in temps, right? And important thing for Python, for t in temps, colon. And then when you go to the new line, do you see how it indented? It actually does it automatically for me, because if I just hit enter, it automatically indents. You have to indent, right? So for Python, these spaces matter here. So just make sure you've done that. So for t in temps, let's just say print is a function I can call, print t. So if I run that, you see how it went through every value here and printed it to the screen, right? First print that, then that, then that, then that, right? That's what a for loop does. So I can repeat stuff a bunch of times. So if I want to run a bunch of simulations and each one I want the temperature to change, you can see where I'm going with this. Instead of calling print, let's call the thing that runs the simulation, right? So basically we're going to want to store, so what we're going to want to do, we're going to want to store our simulations in another list. So we'll have a list of simulation data that'll have these objects that we create, right? These ensemble objects that we've been talking about. So first I create an empty list. Let's call it sims, because it's going to be a bunch of simulations. So sims equals square bracket. So the way you tell Python that, hey, I'm making an object that's a list and I want to fill it later, you give it square brackets like this. So now I'm going to say, what if I wanted to just fill this with the temperatures? The way I could do that is I could say for t in temps, sims.append t. Okay, so this object sims is a list, and that object has a function called append, which means add something else to it, right? So if I have a list of friends and I made a new friend, I could append their name to the end of my list of friends, right? That's appending. So so here let's just append t. So if I do that, let me make a new cell here. If I just want to see what sims now looks like, see now sims has all these values in it because I appended them to it, right? But instead of just appending the temperature, I want to run a simulation and then append the output of that simulation to my list of sims. So that's really what we want to do. Okay, so let's put some simulations inside of our for loop. Well, we've already run one simulation, and the only thing I'm changing is the temperature from one to the next. So let's just copy this entire line here. So let's copy this. All right, this is the one where we ran a single simulation earlier. Well, actually, we needed a little more than that, right? Here we defined the ensemble, and then here we ran the dynamics. So I'm actually just going to copy all of this stuff, and then I'll move some things around, because basically we want the timer to time our entire run of 10. So I just copied all of this, right? So copy that. Command C will copy all that. Make sure you know your copy and paste keyboard commands. So now I go down to, here we go. I'm going to put this inside the loop for now. So if I put this in the loop, for me it's Command V to paste that. Okay, notice how the indenting got messed up, right? Some of these things are out, some of them are in. So just use the tab key or 4 spaces, 1, 2, 3, 4, right? They're equivalent. Some people get real fired up about which one to use. I don't know, I go back and forth. Okay. So instead of test sim, let's call it sim. So this is a list of multiple simulations. This is a single simulation. So, and let's put the start time. Let's put it at the beginning here. so that we start measuring time at the very beginning, because that basically starts the stopwatch, you can think of it as. And then let's put this, okay, we want this to be outside of the for loop. So to make it outside of the loop, so we want it to happen after the loop is done, it has to be not indented. So let's see here. Okay. And so if we're running dynamics on the thing called sim, then that means sim has to be here, right? It says test sim, but we changed the name. So this has to also be, let's copy that, paste it there. Okay, cool. So we're running a simulation, same parameters as before, right? We define an ensemble, same parameters as before, and then we run the simulation here. But we want to change the temperature, right? We don't want to run the same temperature every time. So what we have to do here then is, instead of having temperature equals 1, what do you think it has to be? Think about it for a second. If we're calling t in temps, right, it has to be equal to t. So basically we are going to do a loop. We're doing a for loop over this list of temperatures, right? So first t equals 0.5, then it equals 0.6 repeating, then it equals 0.83 repeating, right? All these numbers. Each time we loop through here, it assigns that value to temperature. So temperature equals T. So it's going to keep doing that. So it's doing that, then it runs dynamics, and then at the very end, it tells us how long it took to run this. So now another thing we could do is, let's see here. Oh, I almost forgot. We have to save these things, right? Remember we talked about earlier, we were appending things, right? Remember I mentioned your list of friends. You make a new friend, append them to the end, right? You add them to the list. Same idea here. So if we have sims, we want to append our output to that. So sims.append, and the thing we want to append is our simulation that we ran here, right? So we're going to append that simulation. And you know, while we're at it, why don't we write, well, this is optional, but if you want to write an XYZ file for every single simulation you run, and remember that runs very quickly, but it'll make a bunch of XYZ files, but I'll do it just to show you. So if, remember we have this command from earlier, I just copied and pasted it. viz.write XYZ for sim, okay. So this will also make an XYZ file for every single simulation. So if we want to go check them out and watch the little balls bouncing around the screen, we can do that. This should do it. So one more time, before we run this thing, let's take a look at it. From top to bottom, what this code cell does, let me expand that slightly. From top to bottom, this code cell, where did it go? There it is. We start a timer, right? So this gives us our initial time and our stopwatch here. We define an empty list called sims. So these are simulations. This is where we're going to store the results of our simulations, right? Because every simulation has this object called ensemble, right? We make a new ensemble, right? Ensemble is an object, which is like a car, right? But each one has a different position in this list. So this is like, you know, storing a bunch of cars in one of those trucks that moves cars around. That's what this list is like, right? Every time I run a simulation, I store that new simulation in this list. So sims equals square brackets for an empty list. Let's see, we run the first simulation. We just call it sim. We run the same parameters as before. The only thing we're changing each time is the temperature. So temperature equals T, and it pulls that from this for loop. So for T in temps, right? And temps is this thing, right? We have you have to put them all together, right? And by the way, if you need to pause this, rewatch things, that's why this is asynchronous. That's why I'm doing it the way I'm doing it. So really take the time to understand this. If you have to rewatch things, if you have to pause it and think about it, do that. All right. So we have a list of temperatures. We're doing a for loop over all of these temperatures. This T right here, we say temperature equals T. That's the parameter we run with. We simulate. So dynamics.run dynamics, right? That's a function I wrote that actually runs the dynamics. So ensemble just initiates an ensemble of molecules. So they haven't gone anywhere yet, but they all have a position and they all have an initial velocity. Right? And the initial velocities, the directions are assigned randomly, and basically the higher the temperature, the faster the velocity is, right? The bigger the magnitude of the velocity is, right? But the direction is random, so randomly assigned. Let's see here. So yeah, so at this point they're just sitting there waiting to go. then run dynamics says, okay, take that ensemble and let's just let time move forward and see what happens, right? So we're going to do that for 1500 steps. We're going to save our information every 5 steps. After this step is done, then we're going to write out the stuff that's in sim here, right? We're going to use write XYZ. That's going to make these XYZ files that we can then open with PyMol or VMD, whatever you like to use, and look at them later. And then importantly, we need to append sim to sims. So if I didn't have this step, this would run 10 times. It would run 10 simulations, and every time it would just overwrite the previous one with the new one. So it would run 10 times. We'd sit there waiting for it, right? And in the end, we'd only have one simulation because we overwrote the simulation data, right? It'd be kind of like if you had to write 3 papers for class and you kept naming them the same thing, and each time you just wrote over your last paper, and then you're like, oh my God, where are my 3 papers? And the most recent one replaced the others, right? So it's like that. Okay, so that's it. So that's the for loop, and then the stuff down here, we just copied that from elsewhere. That's going to tell us how much time went by. And again, don't write these things again. Don't retype things. Cut and paste as much as you can. So make sure you know how to cut and paste on here. All right, I think that's good. Let's try running it and see what happens. This might take. I think this takes more than 5 minutes on my computer. Let's find out. Let's run it. So Shift Enter. Oh wait, you know what? Let me stop it for 1 second. Oh, by the way, if something's running and you want to stop it, hit this little square here. Stops it. One thing I want to do is I want to add a statement. So let's see here. Let's do. Oh, you know what? There's 2 other things I want to do. Okay. Let's create a file name. This, I'm just going to give you this code. So this one, basically what I'm doing here, I'm taking the time and I'm making a file name out of it. All right. So just, let me zoom into this thing so you can really copy this. Really see what you're copying here. There we go. So just copy that exactly, pause it, and copy this line with the file name. What this is going to do is it's going to create a new file name that's based on the temperature. So if the temperature is 1, it'll be like 1.xyz, right? So that you need this to do that. As the details of how it works, it's kind of not worth talking about for the purpose of this particular lab. So I don't want to get too deep into the Python, but if you do want to write the XYZ files, you're going to want to do this. Otherwise, you're going to overwrite it every time if you don't give it a new name. So we're going to call this thing file name. So file name is going to change every time depending on the temperature. So we're going to give it a file name based on the temperature each time. Then let's see here. Run the dynamics. Okay, here we have the file name. So whatever this is gets used as the file name for write XYZ. Another thing I want to add is I want to add a print statement. Let's add a print statement at the very beginning. So you see how this ran simulation step 0 complete, 100 complete, etc. So that's fine for telling me what step I am on the simulation, but which simulation am I on? Right? We're running 10 of these things. So if I want to see which simulation I'm on, let's put a print statement that tells me. So if I say print, let's say beginning simulation for file name. So then this needs to be below file name, right? So let's delete that, or cut it rather, paste it below. There we go. So beginning simulation for file name. So what this is going to do is going to print out to the screen which simulation's running. Okay, I think we have everything now. Let's try running this thing and find out. So I'm in that cell, Shift Enter, beginning simulation for 0.5.xyz. So notice I put a P instead of a dot there. The reason for that is that file names that have a period in them things can happen with them because it thinks the period is telling you the file type. So avoid putting periods in file names. In fact, you should avoid spaces too. I think a lot of operating systems now allow them, And but things can still get funny, especially if you're doing, computational chemistry type things. Just never put spaces in file names or periods. So this is running. We're on the first simulation. So the lowest number was 0.5, right? 0.5. And sure enough, yep, 0.5. So that's the one that's running now. Next one should be 0.6 repeating. This one is not quite done yet. So this thing is running. So there's probably not much point in you watching me watch my computer run the simulations. So I'll just do an edit to the end, and then we'll look at how much time it took then. So you'll see how much time it took, but we don't have to sit there watching my computer. All right, so this thing finished running. So you see that after it outputs a lot of stuff, you kind of get this little scrolly thing here, right? So you can scroll through that. And we see that it took 9 minutes and 8 seconds on my computer. So all 10 simulations took under 10 minutes. So hopefully you get a similar results. Maybe it'll take you 15, 20 minutes, something like that, hopefully at the worst. Cool. So we have all of our simulations now. So now, let's see, and we stored them in an object called sims. So sims is a list of all of our simulation results. So the way you access one simulation from that list is you use square brackets and then you say which one you want. So, and the counting starts at 0. So the first one is actually called 0. The second one is called 1, right? So if I type 0, shift enter, it tells me that it's an ensemble. So this is a list and the first element in it is an ensemble, which is not a surprise, right? We knew that was going to happen because, look, right? We defined ensemble, right? Sim is an ensemble. We do the simulation and then we append it to sims, right? So it seems to have worked, right? And I can check the length of this too, right? So if I type len, that means length. Put that in parentheses and then put what's it called, sims. Shift enter. It's 10. There's 10 simulations. Cool. Everything's working so far. Okay, so now what we're going to do is we need to put the simulation data in a data frame so that we can store it. So we're going to call it LJ data for fit. So this is the Lennard-Jones data that we're going to use for fitting the van der Waals model to it. But we don't need all the data from the simulation, right? Remember when we did that dictionary list thing? It gave us like, I don't know, maybe a dozen different things that are stored in that ensemble. We don't need all of that, right? We need, namely, we need pressures and temperatures, right? So let's make a data frame that stores the pressures and temperatures. So let's see here. The way we do this is we're going to create a pandas data frame. So we do this PD because when I imported pandas, I said import pandas as PD. So our abbreviation for pandas is PD. So PD dot. I typed capital DAT. I'm going to hit tab. There we go, data frame. So it suggests different things. The top one's the one we want, data frame. So data frame, capital D, capital F. The capitals, they matter, right? And parenthesis. And what this is going to do, this is going to create an empty data frame, right? So I can make that thing. And then this particular cell here, we can output what this data frame is here. So if I hit this one, shift enter, there's nothing there, right? Because this is just an empty data frame. So that's why it didn't really give us anything. But we could put stuff into it. So the way we do that is you give the name of the data frame and then square brackets. And then in quotes, I have to put the name of what I want the column to be. So in your head, you think about this almost like you're building an Excel spreadsheet, right? Where you're giving columns one at a time here. So if I want to put temperatures, I'll call it temp. I'm not going to call it T because later there's a function that's just called T in Python for a transpose. It's a matrix thing. Don't worry about it, but that's why I'm not calling it just T. We're going to call it temp. So if I have this temp and then I say equals, then I have to say, what do I want the temp to be? Well, what we're going to do a trick called list comprehension. And this is a Python trick that I just want you to be aware of it for now. I'm going to show you how to type it. So I'm going to give you, you can just follow along and type what I type. But what we're going to do here, what this basically does, list comprehension, it creates a list and fills it at the same time. So remember before we made an empty list and then filled it inside of a for loop? right? We did that in the earlier example. Here we're going to do it in one shot. So here we create the list by typing the 2 square brackets here. Then inside of that, we're going to put the for loop. So let's type that. So let's say the way you do it here, s.temperature for s in sims. So that's what you type. And just to tell you how to think about it, look at the for loop first. When you're first getting used to doing list comprehension, start with the for loop when you read it. And you say, okay, for s in sims. So okay, I'm going to step through my list of simulations called sims. And for, the one that I'm on at the time, I call that s. And then for s, I want to pull out the temperature, right? Because remember, there was like those maybe 12 different things we could pull out of any simulation data. And I want to pull out the temperature. So s.temperature will do that. So if I do that, and then I execute this one, see how I have a column for temperature now. Now I have all my temperatures, all 10 temperatures that I ran. Notice they're numbered 0 through 9, right? Not 1 through 10. This is a Python thing. If anything that's counting in Python, you start at 0. The first thing is 0. Okay, so that's the temperature. Now we want to do the same thing for pressure. So I'm just going to copy that line and paste it, because why start from nothing, right? Because it's going to be kind of the same, a very similar process. For this, I'll just call it P for pressure. And instead of pulling out the temperature here from S, I'm going to pull out the pressure. Pressure for S in sims. And that should do it. So let's run that, run this one. Now you see we have 2 columns. We have temperature and pressure. So that's what we need to do for this step. So this particular step here for storing the simulation data in a data frame. So we've done that now. We've taken the data that we want and put it in a data frame. And so here's a code that I just give you. For most of the plotting codes, I'm just giving them to you. Because, like I said, this is for people who've maybe never done anything in Python before. Like this might be your first time in doing things with Python. I don't want it to be too overwhelming. So let's uncomment this code that I gave you. And this is why it's important that you use the same names that I use so that the other things work, right? Because there are things that you can name them anything you want, but then you have to change that name later too. So don't have too much fun with the names here. Use the same names I use. So let's see. So if we uncomment this, and note this uses LJ data for fit, temperature. See, I pull out the temperature, .temp, and then .p. If I run this, it produces a plot. Cool. So we see there's some kind of uncertainty in this, right? As I've talked about, this is a constant energy simulation. So temperature is actually going to fluctuate, and that's okay. It has to, right? This is the laws of physics at work here. But we see that the overall trend here is that it gets hotter, the pressure goes up, and the volume's constant, right? Like if you were, I don't know why you would do this, but if you had like a can of soda and you put that in a bonfire, right? The can of soda wants to hold constant volume, but the pressure inside is going to go up, and then maybe the soda comes flying out of it, right? This could be something this would be a dumb thing to do. Don't do it. But you can imagine that would happen, right? If you heat something, the pressure inside goes up if the volume can expand, right? So if the volume is constant, temperature goes up, pressure must go up. So this is doing something reasonable, right? So this is always good. When you're writing a simulation, you're basically creating like a world where things happen, right? You've given it laws of physics. So just to see something reasonable like this is a very nice thing. You're like, okay, the simulation is not completely crazy. So yeah, so heating it up, pressure goes up, temperature goes up, pressure goes up. Cool. So this is a trend that we've seen, that running our simulation at higher temperatures with everything else the same, the pressure does go up. Cool. Now we want to fit a van der Waals model to this. So basically, the first thing we want is we want a function that's going to get van der Waals pressure. So remember, let's find it real quick. I already did the algebra for you. If we look for it, if we find it here. There it is. This is the algebra here, or this is the expression for pressure given that we know the A and B parameters for our van der Waals equation, and also we know the reduced volume, right, V over N, and also temperature. So if I give these things to this function, it tells me the pressure, right, as predicted by van der Waals. So this is the function we want. So we'll scroll back and forth to look at that. Okay, so down here what we want to do, where is it? Down here, we want to define a function that I'll give it these things, and it gives me back the pressure. So I give it the T, the V, the N, the A, and the B. It gives me pressure, right? According to van der Waals' law, van der Waals law. So, or the van der Waals model. So here, the way you define a function, right? So here we're creating a function, right? You've seen me use functions, but now we're actually creating one. DEF, define. So we're going to define get van der Waals pressure is the name of the function. Again, don't change these names. Then if I hit enter, see how it automatically indents? So anything I want the function to do needs to go inside of this thing. Okay, so the first thing that we want to do is, the volume that we're using is a reduced volume, right? It's not just regular volume, right? So let's define that first as little v, just like it is in the equation. So little v equals big V divided by n. Cool. So first step's done. We've got our little v defined. The next thing is we want to do this math. Where'd it go? This, right? So we've got all of this stuff. This times that, right? Basically, we want all of this math being done, right? There's some addition, some subtraction, and some division, right? So, we probably want some stuff in parentheses, right? So let's see. The way we do that is like this. So I have one that I worked out earlier to make sure that everything works. And it looks like that, right? So if you look at that, that equation, right? Oopsies. Right? All this stuff divided by that, right? Now, if we look down here, I've typed that same thing out, right? I'll zoom in so you can see it. So looking at this, we've got negative a times b plus a times little v minus t times little v. Now we got asterisk, asterisk 2. So in Python, if you have an exponent, you do double asterisk, means an exponent. So this right here, this v asterisk asterisk 2 means v squared. So that's how you tell Python to square something, right? In some programming languages, it's that little caret thing, right? But not in Python. Two asterisks. So that's an exponent. So all of this gets divided by all of this. All right. So move very carefully, very slowly. Make sure that this really reflects the correct equation, right? You have to get this correct. So so that gets us p. But we want this function to give us that then. So then we have to tell it return p. So now we've defined a van der Waals pressure function. So basically what this does, we give it all the van der Waals parameters it needs, and it tells us what the pressure would be if all this stuff is true. So, we're taking math and we're translating it into computer code. So the reason this is in the exercise, that's a big part of what computational chemists do. We have to get really good at this of translating math into computer code and backward. Translate, and then if we get something to work in a computer code, then we have to say, okay, mathematically, what did I just do? And then you have to explain it in equations. So when we write papers, research papers and stuff, we go back and forth between computer code and equations all the time. So I wanted you to get a little taste for doing that. So now we've defined a function that if I give it a temperature, volume, number of molecules, and then the A and B parameters, it tells me the pressure. Great. Now we have some functions here that I'm just giving these to. I didn't even comment them out. I'm just straight up giving you the chi-squared score, and then a function, and then a function here that will test all of the A values. So basically, remember I said that we're going to find the best A value, but just trying a bunch of them and see see which ones get closest to the real answer. So we're just going to have to execute this. So shift enter, and that'll execute this get chi-squared, right? This is a least squares fit. This is the trick we're using here. And then we have test A values. This function will test an entire list of simulations. So we have a list of simulations called sims. So we'll pass that to that function. And then we also have we also need a list of A's that we want to try, right? So we're going to try a whole bunch of them. Well, we have to decide what to try. And then of course B. The van der Waals equation has a parameter B. We've already calculated it, right? You've calculated yours. I believe I made up a fake one. I think I called it 0.8. If fact, if I type B, shift enter, yeah, it's 0.8. I've set it to 0.8. Yours will be whatever you get from calculating a volume, right, of a sphere. Well, you go back to that part, but you have to calculate B yourself, right? But the one I used just for our example is 0.8. So that is there. And so we just have to run this test A values. But first, we need to get an A list. We need a list of A's we want to try. Well, I'm going to tell you that, you know, a reasonable range to try is -1 to 1. And we can adjust this if we think we need to. But we're going to, let's define an A list going from -1 to 1. Well, and we want to make 200 of these things. So we'll print it, but then we probably want to get rid of that print statement because it's going to be a lot of numbers. But remember, we've done this earlier. We got a range earlier. So if you remember, this was our linspace command, right? np.linspace, and you give the range. So -1 to 1, and then how many numbers you want, which is going to be 200. So -1 to 1 and 200. Okay, there's all the numbers, right? So this just generated all these numbers for us. -1's the first, 1 is the last. Cool. So we don't need this print statement anymore. I'll comment it out. There we go. I made a comment. Now it doesn't execute. So now let's see here. Okay, so we have an A list. Now we have this function that will test our A list for us. So I've given you that as well. So we have sims as our list of simulations. We have A list, which we've just created here. And our value of B, which we've assigned earlier in the notebook, right? Which is, it's 0.8, but we'll pass it as B. Now if we run that, okay, it's already done. Let's plot that. Let's see what this thing looks like. So I've given you the code for plotting here. Uncomment that, run it. Okay, so we see that there's definitely a minimum here, right? Let's go a little bit lower though, because we see that like, it looks like we probably hit the minimum, but I'm not 100% sure. So let's make this a little lower. Let's go -2 to 1, something like that. Shift enter, shift enter. There we go. Now we've definitely found the minimum, right? And we can even add more points to this if we want, you know, because now we've gone a bigger range. So now the points aren't as close together. I can get more. Let's just increase that to 500. This function's really fast, so we can kind of go crazy with it. All right, so these are individual points. If I zoom in really close, well, it's hard to see because there's so many. Let's do 100 real quick. There we go. You see how these are individual points, right? These are different values of A that we're trying. So those are all little circles. It's not a solid line. But let's put it back up to 500 because I want good precision here, right? If we try a bunch of these real close together, then we can get the best one and you know, feel more confident that it's the best one. We didn't maybe skip over the best one. So at 500, shift enter, shift enter, shift enter, shift enter. There we go. Now I see a clear minimum, right? So we know that our least squares fit. We've definitely bounded where the minimum is. So this is good. Okay. So if we eyeball this thing, we see that the best value is somewhere between -0.5 and -1, somewhere. But we don't want to eyeball things, right? We're using a computer here. The computer can find it for us. So what we're going to do is we're going to use, where is it? The NumPy function argmin. So basically what argmin tells us is it'll tell us like where something is. So if I have a list of numbers, let's say I have a list of numbers and I want to know the lowest number, argmin will tell me which position that's in, right? So if I have, let's imagine I have an array of 10 numbers, right? So I have these 10 numbers and the third one's the smallest number. If I use argmin, it gives me the number 2 back, right? Because it goes 0, 1, 2, right? So the third position is where the lowest one is, and it tells me that with a 2, right? You get used to counting from 0. But okay, so this is what we're going to do here. So we're going to use numpy.argmin. So np.arg tab. See, we got different things. We want min, argmin, and we're going to get argmin of, where is it? We want to get it of the lowest value of chi. Okay, so we want the lowest value of chi. We want to know where that is. So, and we're gonna kind of build this out slowly. So we want to know where that is, but we want to know it in, where is it? ATEST-DF. First, let's take a peek at ATEST-DF. So remember I told you a data frame is kind of like, it's almost like an Excel spreadsheet that we don't have to look at the whole thing if we don't want to, right? So if I test df, let's say I do want to look at the whole thing, shift enter. So there's a whole bunch of stuff. In fact, it won't show me all of it because I've got 500 rows here. But one thing you can do if you just want to see part of it, if you imagine your data frame is hiding behind a wall and it just peeks its head out the top, right? There's a function called head, right? So you go dot head, 2 parentheses, right? Make sure they close. Shift enter. There we go. And that just shows us the top of it. So we have an a value and a chi-squared. Okay. So I could get the head, or I can of the entire data frame, or I could take only. Let's say I only want the chi values. So if I only want the chi values, so atest.df.chi-squared, right? Dot head. Shift enter. See, now it only shows me the first 5 of only the chi-squareds, right? So if I were to get only the chi-squareds, this is the command, right? And we've done this before with data frames, right? We have the name of the data frame dot and then the column we want, which is chi-squared, XISQ, right? So let me copy that real quick. So I cut that. I'm going to put that here. So now if I run the argument on that, it tells me where it is. It's in position 200. How about that? Exactly 200. So at position 200 is where the lowest chi value is, right? And that's the whole point of least squared fit, is which one has the least square. Well, it's the number at position 200. Okay, so that's where it is. So going down that data frame, it's the 200th row. So the way I get the 200th row, I can now put a function around this. So this whole thing is giving me 200. So if I put square brackets around that now, and I put the name of the data frame here, copy that, and then if I want to pull out one row by its number like this, I go .iloc, so the index location. So then the position where it is known as an index, and then its location, that's where it is. So the thing that's at location 200, shift enter, and it shows me what it is. So chi-squared value is 0.005063, and then of course a is equal to minus 0.797595. So that's just my particular simulation that I ran, and I'm even using like a bogus value of b, right? So your number is going to be different. And in fact, if you're working with a friend, I encourage you to do that. But you might get different numbers, and that's okay. They shouldn't be wildly different, but they can be a little different. Let's see. Okay, so now we're going to get one thing we can do here. We can even take this another step. So let's say, actually, I'm going to move this cell up one. So if you hit this up arrow, it moved it up, see? So now below that, what if I copy this thing? What if I only want the a value? So I found where the minimum chi value is, but now the thing I want out of this is a. So I can actually go .a. And there it is. So this number right here, right? That's this number. It's just truncated in this printout, right? But this is the number. So this thing right here, this is our best A. So let's copy that, put it here with best A, and run that. Okay, so now best A is this number. Cool. So now we've stored the best A value. So we've tried, how many did we try? 200, 500? We tried 500 different A values. This is the best one, right? And from this plot, we see that we've tried them on both sides. We've made it, we've definitely found the minimum here. Okay, so we have our value. Okay, now we want to create a data frame that's going to hold all of these predictions. So let's see here. So let's make a list here. So I've given you a lot of the code. 1, 2, 3, 4. Okay, that's indented correctly. Okay, so VDW points, what we need to do here is we need to create a list that holds the temperature and the pressure. So we're going to append the temperature and the pressure. So it's we're going to have a temp here and a pressure there, right? But we have to give it the names that Python's going to know, right? So this is what we're appending, pairs of temperatures and pressures. But if we're looping over sim, right? This was in the code I gave you, right? So let me zoom in. So we're looping over all the sims, and as we loop, we call the thing sim, right? So as I said, like we have this list, we're moving along the list, but when we refer to the one that we're on at that time, we're calling it sim. That we gave it that name right here. So let's see here. So we do append. We're going to go sim.temperature, right? Because the simulations we're moving along, these are these ensemble objects, and we can pull out the temperature by just saying .temperature. The other thing we need is we need to get the van der Waals pressure. So for that one, we need to call our function get van der Waals pressure. Let me copy that. Remember, use copy paste. Don't write these things out if you don't have to. In fact, let me copy all of that. So we're going to copy this van der Waals pressure. Where is it? There it is. So instead of this P here, let's put van der Waals pressure. And we have to pass it these different things. So we need the temperature, the volume, the number, all these things. So basically, we're going to pull all these from the sim. So our first we need our temperature. So sim temperature, copy, paste. And the volume and the number we're going to get in the same way. So I'm just going to paste that like this and like that. So this one was supposed to be volume. So VOL tab. Oh, it doesn't know to finish it. VOL UME, because it doesn't necessarily know what sim is. So that's why it wouldn't finish it for me. Temperature, volume, and then what was it? Let's look at the function again. The function says to give us, where'd it go? Hang on, I passed it. There it is. Temperature, volume, number, AB. Temperature, volume, number, AB. Okay. Temperature, volume, number. So the number, to get the number is NMOL. And then A, we want to use the best A. So best A. And then B is defined elsewhere. So we can just put the letter B there and that'll do it. So this should be good now. So if I execute that, let's take a peek at what this looks like. So if I go, and notice I gave you this code, right? We made it a data frame with this code here. So if I go, see this name here, VDWDF. So VDWDF. If I say .head to take a peek at this, there it is. We've got temperatures and we've got pressures. Good. This looks reasonable. I think we're okay so far. So now what are we going to do? Now we want to plot these things. And again, I've given you this completely. So this is here. All you have to do is uncomment it. So delete. Okay, shift enter. Voila, look at that. So here we have a fit where the orange line here, and your colors may come out different. It doesn't matter what the colors are, but the line is the prediction made by the van der Waals equation. And then the dots are the actual temperature and pressure points, right? So X is the temperature, Y is the pressure. So we see that this thing did a pretty good job of finding it for us, right? So now just to kind of wrap it all up in the end, our whole goal here was to say like, okay, we have these Lennard-Jones simulations. Can we find a van der Waals law that will approximately give us the same predictions of pressure? And the answer is yeah, we can get pretty close, right? This is going to be pretty close, and there's some wiggle in these anyway. So this isn't bad at all. So basically, the last thing you want to do then is see how it says A equals your answer, B equals your answer. These parameters are the things we found, right? So in case we forgot what they are, our best A, actually let's print them both. So if I say print best A, print B, our values are this and this. So we want to take these values. So our best A is this. We'll just truncate it here for now. And if I double click this, what was that? That was A. The answer for A goes here. See, here's your answer. And remember, I double clicked that. I double clicked on this thing to edit it. Control V to paste it, or Command V. And then your answer here, that's going to be 0.8. So your answer is 0.8. And I hit Shift Enter. And there we have it. So the value for A that I calculated here was minus 0.79 whatever, and the B is 0.8. So hopefully you had some fun running the simulations. I hope you enjoyed this some. I think it's really cool work to do. Obviously, it's what I've devoted my career to, so obviously I'm biased. Yeah, all right. Well, I hope you enjoyed it, and if you're an instructor and you're checking this out and you want to use this lab for your class, feel free to send me an email. I'm happy to share files. All right. Take care, everybody.